Welcome everybody, and thank you for coming despite the weather today in Rabat. So exceptionally, we have a rainy Rabat since 3 days. So Tristan Tomala, my great friend Tristan Tomala is presenting today at the Game Theory Seminar. His paper Correlated Equilibria for Anonymous Large Games with my other colleague and friends, Frédéric Kosler and Marco Scarsini. So I know Tristan since I started my PhD because he was finishing, I think, approximately the moment I was starting my PhD. And then we were colleagues at Dauphine for some moments because after my PhD, I was in Dauphine for 1 year as Ater, I think. But we are friends since a long period of time. We have even some papers together. And so Tristan was after his PhD at Paris 1. He was maître de conférence at Université Paris Dauphine, then professor in mathematics, then professor of economics at HEC Paris. Since then, he transformed himself from mathematician to economist, as many game theorists, and he's working a lot on value information, repeated game, communication, and he's giving this week a lecture at the Game Theory Center as part of the PhD program, and at the same time, he will be giving the seminar today. And I'm very happy to have him here in Rabat. Tristan.
Okay, thank you. Thank you very much, Rida. Thank you for inviting me to teach in your wonderful program and for inviting me to present today at your seminar. I just have one correction to what you just said. I don't think of myself as an economist. I still think of myself as a mathematician. An economist should know something about interest rate and unemployment and stuff, and I don't know nothing about this, but I know a few things about some game theory models, so I think still applied mathematics. Anyway, thank you all for being here. So I will present you a research project with my colleague Frédéric Kessler, who is also at HEC, and my colleague and friend Marco Scarsini. Frédéric is also my friend, by the way, who is in Rome. And this is about correlated equilibria for anonymous large games. That's the title of the presentation today. Another title could be information design for a game with a large number of players. So here is some element of motivation. So there is, since the last 10 years, a whole literature in game and economic theory about information design, which basically thinks about how the design of information structure, the design of information to players shapes their equilibrium behavior. So that's a kind of parallel approach to mechanism design, which is much better known. Mechanism design is something like how to choose best the rules of the game in order to induce such and such outcome that would be desirable according to some criterion. And information design basically asks the same type of questions, but does not play with the nature or the actions in the game, but play with the information that is given to players. So if you want to think about when information would be relevant in a game with a large number of players, think of traffic. Think of congestion in traffic problems. So I'm not sure whether you have congestion problem here in Rabat, but there is? At some specific time of the day, there is congestion. I can tell you there is a lot of congestion in the Paris area. Jose Correa, who was in this seminar and I think in this program, who is working in Chile in Chile, they have a lot of congestion problem in Santiago. There is a huge amount of congestion, as far as I know, in Istanbul and in many such cities. So, and now when we drive, we use information systems because you connect on Google Map, on Waze, on whatever application you like best, who tells you what is the fastest road that you want to take. And so this app is an information provider. It provides information about driving condition to drivers. And it's easy to, perhaps, if you think about it, it's not completely obvious how you should send information to drivers. Because suppose that there are two ways, two routes that you can drive, route A and route B, and now you know that there is an accident on route A, so route A is going to be congested. So what do you want to do? Do you want to tell all people, oh, everyone should go route B? But if everyone goes route B, there will be a jam on route B. So probably it would be best that the traffic would, get a little bit dispersed between route A and route B. So it's not completely obvious what should be the best information that you want to send to drivers in this. So I will give you example about that. So that's a motivating example in terms of information and also in terms of large games, because I'm going to talk about large games where there are so many players that your personal influence on the driving condition is negligible. It's not because you're there that there is a jam. There is a jam because there are so many drivers. All right? Okay, so on these slides, you have a number of other application of such problems. So think about externalities, think about vaccination, think about random matching in large population, and so on and so forth. So you can see the last line, the decision about self-isolating to get vaccinated. And if you read that, you can think that you can reconstruct that's a project we started during the COVID period. So we were kind of influenced also by the story at the time. Now it's a little bit behind us, gladly. All right. This is a theory paper, so I'm not going to give you concrete application. That's not the point, but rather develop mathematical tools, mathematical models for modeling those situations. Okay. So these are the objectives what we're going to talk about. So how to design information to large set of players, that was my introduction. I was going to propose a definition of correlated equilibria for nonatomic games. One first result is going to be a justification of the notion we're going to propose. I mean, a game with a continuum set of players makes some sense if it is an approximation of a game with finitely many players, but the numbers being very large. So this will be our first result to show that there is some form of convergence, that indeed the continuous model that we're going to propose is the limit case of a large but game with finite number of players. I'm going first to talk about complete information, then incomplete information, and give some result about optimal information structure. Okay, so that's roughly the plan. I'm not sure I will cover everything in the presentation today. By the way, I don't keep track of the time, so please signal me when you want me to stop here. But okay, just give me some signal, maybe 10 minutes before, something like that. All right. So yeah, let me start with a model of complete information, some examples, and some first result. All right. So here is the model of, let me call them anonymous game. You can call them symmetric games, large games. So here's the model. So what's going to be continuous in this model are players. That is, there is a set of players, which is a continuous set with mass 1. All right? So there is a mass 1 of players. If you want to have a more precise model of a mathematical model of that, think of the set of players as, let's say, for instance, the unit interval with the Lebesgue measure, or any non-atomic probability space. But my co-author, Marco Scarsini, doesn't like that because he says we should not impose some condition on the set of players. Players are just a continuous number of them, and everyone has mass 0. That's the point, right? But he says, well, if you start putting players on the line, then you start to introduce correlation between players, some distance, and this has nothing to do with what we're going to talk about. So continuous set of players, everyone is negligible. Okay. Finitely many actions. I'm only considering finitely many actions, okay? And that's one reason of that is for technical simplicity. Okay, now, what's going to take the role of a strategy profile we are going to call a flow. So in a normal game, in a finite player games, everyone chooses an action, and then you have a list of actions listed by the players, and you call that an action profile, right? Or strategy profile. Here we're going to call that a flow. So there is a number of actions. The set of action is common to everyone, okay? So think about the routes, let's say from going to here to downtown Rabat, and look at how many possible routes that you can take. That's A. That's the finite set, the same set for everyone. And then the players, they spread out themselves around those actions. So X, we are going to call that a flow. And mathematically, that's a distribution of actions. It's not a probability distribution. It's a set of proportions. What is a proportion? X1 of people choosing action 1, X2 of people choosing action 2, and so on and so forth. All right? So it's a set of mass of players choosing the various action. And by assumption, the total mass of players is 1. So the sum of the mass of the masses of players over the various action must be 1. So that's X. Okay. And now, when anyone that chooses action A pays a cost, and this cost CA of X, that's the cost paid by any player who chooses action A given the flow X. All right? So, which means that the cost that you're going to pay depends on which action you took and depends on what are the proportion of people having this or that behavior. All right? If you think about routing, again, that's not the only example that we have in mind, but you could say, I take route A, so I'm going to pay a cost or maybe suffer a time travel. That depends only on the number of people taking route A. And if you take route B, you're going to pay a cost that depends only on the number of people who take route B. But that's a particular case. More generally, the cost that you pay choosing action A could also depend on the number of people choosing action B. Okay? In terms of routing, for instance, it could be that two routes, they have some common segment. So maybe you have two routes, but there is a common bottleneck where the jam is going to be everyone going to suffer from it. So even if you took route B, perhaps you create a jam for people who took route A. All right? So that's why this function CA depends on everything. Assumption, this is a continuous function. CA is a continuous function. Following remark, I call that a cost, and we are going to have games where players do not maximize utility, but they minimize costs instead. There is no particular interpretation to that. What's the utility? That's the opposite of the cost. So put a minus sign, call U is called minus C, and you get a game where people maximize utility. Okay? So cost is just the negative of utility, nothing more. It's just that, you know, in the literature on congestion game, on routing game, it's more usual to talk about cost, but it doesn't change anything to the definition that we can give. All right. So, yeah, I already talked about I already talked about routing game a bit. Yeah, so in routing games, typically you would have a cost function per road segment. You would say that a route, a path from your origin to the destination is a succession of road segments, right? And perhaps a road segment is comprised in several different paths. So when you calculate your whole cost on some path, you need first to sum across all the edges that you traverse to get along the path. But on all the edges, you need to sum all the people who take the various route that comprises this edge. But anyway, that's just that's a particular case. That's an important case. That's a particular case anyhow. All right. Nash equilibrium. Nash equilibrium for this game. It is common in this literature to call that the wardrop equilibrium. But it is Nash equilibrium. There is a very wonderful book about that, about games of population, written by William Sandholm, which regrettably passed away at a young age. But he was a brilliant American researcher who worked on learning and dynamics in game, and he has a full book on this game with large population, and Sandholm called that just Nash equilibrium. But, you know, in this literature on congestion game, it is common to call that wardrop equilibrium. This is the definition. What is an equilibrium? It is a flow X. So again, X is a set of proportion of players playing this and that action. And you can read the first line, that's the Nash equilibrium condition, which says that there is a positive flow. Is there a light on that? Okay. There is a positive flow on action A only when A is optimal. Okay? So I am an individual player, my mass is 0, right? So X, there are this percentage of people taking route A, that percentage of people taking route B. Whatever I do doesn't change X, right? So what am I going to do? I am going to take the action that has the least cost, all right? So in equilibrium, it must be that the only action that receive positive flow are the ones who have the least cost. Otherwise, it's not an equilibrium. Make sense? Okay. So that's the definition of wardrop. You can check that it's equivalent to this for any pair of action A and B, XA multiplies C of X less or equal to XA multiplies CB of X. All right. It's easy to see that these two formulations are equivalent because either XA is positive, in which case you get this, or XA is 0, and then this inequality is trivially satisfied. Okay? That's a simple but important remark. Okay. Under the assumption that I made, this exists. This exists, you applied Kakutani fixed point theorem to this correspondence, and you get existence, right? You can remark that given X, given a flow X, you fix the vector of costs, right? The vector of costs is fixed now. These are just numbers. And you look at the distribution of an action that minimizes this sum. All right? So what's a wardrop equilibrium? That's just X such that it puts positive mass, not probability, positive mass only when this thing is a minimum. That's when you minimize this. This is a linear program, right? When X is fixed, these are fixed numbers. When you minimize over Z, this is a linear program. So Z puts positive mass only on the A's where this number is the smallest. And if X is a solution to this problem, when C of X is fixed, that's exactly a wardrop equilibrium. And it's easy to see that's what we can call the Kakutani correspondence. That is one that satisfies the conditions of the theorem of Kakutani. All right, this exists. Fine. Okay. Example. This is an example that I use. I just take 2 minutes to speak about it because that's where we are going to show that having a correlated equilibrium improves upon Nash equilibria. So this is called the L-Farrell bar. So there are two strategies, two actions. You can stay at home or you can go at the bar. And staying at home gives you a constant payoff. Well, this is cost, but this gives you a constant cost. You know how much this gives you to stay at home. The cost is 1. Now you can go to the bar. And the thing is that if you look at the cost of action B, that's like this, decreasing and then increasing, which means what? When the bar is empty, that's not fun. You don't want to go. When the bar is full, that's not fun. There's too much noise. You don't want to go. What's best is when there is exactly half of the population at the bar. That's where you want to go. But that's not an equilibrium. Because if you say just half of the population goes to the bar, then everyone who stays at home wants to go to the bar. So what are the equilibria? There are 3, and you can see them, the 3 black dots. Either everyone's at home. That's an equilibrium, because if everyone's at home by yourself, what's the point of going to the bar? Or the proportion of people at the bar is exactly such that the cost is the same. Okay? So there are 3 equilibria. Right? There are 3 wardrop equilibria of this game. Now you can check that the cost, it's easy to see on that picture. What's the cost of everyone, of every player in any equilibria? That's 1. Everyone pays the cost 1, no matter what is the equilibrium. So if you calculate the total cost, which is the sum of cost across all the population, everyone pays 1. There is a mass 1 of players, so the total cost is 1. Right. It would be better that half of the population would stay at home, half of the population would go to the bar, because that would achieve a higher total cost. Socially, it would be better, because half of the population would pay 0, half of the population would pay 1, and therefore, in total, that would be 1/2. Okay? So can we get that? Now, obviously, without some intervention, we can't. Okay, so here is our definition. That's one contribution that we propose in this work. A definition of correlated equilibrium in this context. So let us call that a correlated wardrop equilibrium. So just taking a minute, I don't know if you're familiar with the notion of correlated equilibrium in a normal game, in an n-player game, but just in one sentence, what is a correlated equilibrium in a n-player game? That would be a distribution of an action profile, which is correlated with the property that if you instruct player I to choose action AI, then player I calculates its expected payoff conditional on the recommendation of playing AI, and he says, yeah, that's optimal to play AI. That's a correlated equilibrium. A Nash equilibrium is a particular case of a correlated equilibrium. So here, basically, we are saying the same. So a correlated wardrop equilibrium is a distribution over action flows. So recall that X is a set of action flows. That was the simplex over actions. So a distribution over action flows with the following property. The expectation of XA of X less or equal to the expectation of XA of X. So what's the interpretation of that? The interpretation is the following. There is a sort of correlator or mediator who draws, the mediator draws at random a flow according to mu, but that's not the only thing he does. The other thing that he does is that, so he draws a flow over action, and then he recommends the action to a random subset. Okay? So this means that in this equation, mu of x represents the probability that the mediator draws flow x, and xa represents the probability that a specific player be recommended action A. Okay? You see, so if you have this interpretation in mind, the left-hand side is what is my expected payoff, what is my expected cost when I am recommended action A and I choose action A, whereas the left-hand side would be what is my expected cost when I'm recommended action A, but I choose action B instead. All right? That's the interpretation. To be perfectly, perhaps a little bit clearer, but I don't think, perhaps it would be slightly clearer if I would divide throughout by the total probability of action A, which I didn't. So suppose you would divide both sides of this equation by the total probability of action A. Then that would be exactly the expected cost of playing A conditional on being recommended A, less or equal to the expected cost of playing B conditional on being recommended A. But I did not do that. I did not divide by the total probability of A because it doesn't change anything, because either this total probability is positive, then this is the same inequality, or this total probability is 0, then we have 0 on both sides. Okay? And like for correlated equilibria, this set of inequality is linear in mu with respect to mu. Okay, so you can see those bullet points. That's exactly what they say. So yeah, that's exactly what I said. Notice that this definition avoids the problem. So there is a reason why we say there is a continuum of players with mass 1, but we don't make it specific what it means. If I was to say that the set of players was a measurable set with a non-atomic probability distribution, you would ask me, how do you select at random a subset of mass xa? And I would say, in general, I don't know. Perhaps you can do it, perhaps not, I don't know. With the unit interval or the unit circle, I could do that, you know. But this would be somehow an artificial procedure. So that's what we don't want to do. All right. Okay, so this set of equilibria contains the set of wardrop equilibria, and any distribution of a wardrop equilibria, namely Henry randomization of a random equilibria, so the convex hull of wardrop equilibria, if you prefer, is a subset of this. Yes?
So you should probably call it canonical correlated equilibrium, but just technical, because somehow it's a canonical. You express it in terms of recommendation to play an action, and it's a direct mechanism somehow. So
you're right.
I
agree with you somehow. In a sense, you are right. We could call it canonical correlated equilibrium because that's what it is. But we didn't do that for a reason that what's a non-canonical correlated equilibrium then? And the answer is I don't know. Yeah, the answer is I don't know, because if you look at the theory of Meyerson and Forge, or Oman, Meyerson, Forge, of communication, correlated equilibria, and so on and so forth, they have a list, they have a definition of what is a general correlation device, communication device, and so on and so forth. And with that, they are able to show some revelation principle and to say everything boils down to this. Now, what would be a very, very general class of correlation mechanism with a continuum of players? I don't know. And I'm not sure I want to enter into that. I mean, we avoid this problem.
clever to go like this because otherwise it's too complete. It's that's why perhaps people didn't do it to start with, because it's not obvious to do it directly in the general framework.
Yeah. And if maybe you know there are some papers who do that in general equilibrium or in macro. People like Carmona, for instance, they go into this. They go into a general set of players, general set of signals, and so on and so forth, and it becomes extremely technical. And at some point, you're never sure that you have exhausted all. When everything is finite, with the, let's say, the approach of Meyerson, you know that you have exhausted all possibilities. But in this general case, how do you know that you cannot find a more general thing?
If you have you connect this to finitely many players, then it's fine, because as soon as you have finitely many players,
yes,
you know that it works, and
yes,
if your model is the limit, then
exactly.
then
so
it's a way to justify this.
Yeah, that's exactly what I'm going to show you next. And also, we have looked at other definitions of correlated equilibria for games with infinite players. So there is that a little bit in the paper of Hart and Schmeidler. And you can check that all the correlated equilibria in the sense of Hart and Schmeidler, the outcome would satisfy this. So I would be surprised if in this context where you have finite set of actions, you would find another definition of correlated equilibrium such that the outcome would be outside of this set. I would be surprised. Okay, so in the example, in the game of El Farol, you have an improvement upon wardrop equilibria if you have a mediator who randomizes between the two flows, everyone is at home, or exactly half of the population goes to the bar. So everyone is at home, that's 1, 0, it's the one wardrop equilibrium. Exactly half of the population goes at the bar, that's the Pareto optimal outcome, but that's not an equilibrium. However, if the mediator randomizes between these two outcomes with the appropriate probabilities, namely 1/3, 2/3, it's going to make sure that when you get your recommendation, you want to obey it. So you can check that. For instance, suppose you recommended A. So what can happen? There is a probability 1/3 that this recommendation comes from 1, 0. Namely, everyone stays at home. Okay? So with probability 1/3, the flow is everyone stays at home. So this is the one here. Everyone, in particular, you stays at home. And you have the cost of staying at home, which is 1. But with probability 2/3, this is drawn from the recommendation 1/2, 1/2. So we have probability 1/2. So with this flow 1/2, 1/2, half of the population is recommended to stay at home. Okay? So with probability half, you're being recommended to stay at home. And then, to be more precise, with probability half, with probability half, you're recommended to stay at home. So you stay at home, and again, you get 1. So in total, that's 2/3. All right? Now, suppose that you deviate from the recommendation. So with probability 1/3, you get, you play B instead, all right? But then, if you go to the bar when everyone is at home, this is very bad for you. Then you get a high cost. With probability 2/3, you get to the bar in this case. So here you get 0. But then in total, that's 2, that's 1/3, that's again 2/3. So you're indifferent. So basically, when you're being, the numbers here are chosen so that when you're being told to stay at home, you're indifferent between staying at home or going to the bar. All right? But of course, if you're being told to go to the bar, you're very happy. If you're being told to go to the bar, you know that you're in the case where you're the happy few. Okay? This is the happy few case. You just have half of the population who have the special ticket to get to the special night, and you're one of the happy few, of course, you're very happy. Okay? But in the first case, when you're being told to stay at home, you think, okay, perhaps everyone is at home, but perhaps they're at the bar, but the probabilities are such that you're exactly indifferent. All right? So that's a correlated equilibrium, and that's better than that's better than all wardrobe. Okay. Yes?
Implies that each player knows the correlated equilibrium from the mediator.
Correct.
They know it.
Correct. Yes. Indeed. Indeed. That is these probabilities. Yes. Yes, 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 yes. You're right. You're right. And if you think that's a lot to assume from knowledge of the players, I agree with that. But that's the notion of correlated equilibrium. Yeah, you're perfectly right. Okay. So here is the approximation result. How much time do I have, Frida?
Half an hour.
Half an hour? Okay. I will show you the proof. It's not difficult. Okay. So here is the approximation game. So I'm going to introduce an approximation game with two parameters, n and w. N is the number of players. It's going to tend to infinity. W is a sequence of weights. So Wi is going to be the weight of player I in the n-player game. And by assumption, the sum of the weights equal 1 because we have the total mass of player, which is 1. Okay? So if you think that now you have the routing traffic, in the limit game, everyone has mass 0. But now that's not exactly right in reality. In reality, everyone has some mass, like the biggest your car, the biggest the truck that you're driving, the more mass that you have. All right? Okay. So now this is an n-player game, and the set of action is the same. And now every player 1 up to n chooses an action, AI. This results in an action profile A. And with that action profile, you can calculate the flow. So what is the flow on a particular action? That's the total weight of players who choose that action. Okay? So, sorry, but perhaps the notation is slightly confusing. A in this slide denotes a action profile, 1 per player. E denotes one specific action. So XE of A, that's what's the total flow, the total mass of players who choose action E. That's the sum of the weights of those players. Okay. So here is the result. Suppose that n tends to infinity, and suppose that all weights tend to 0. Then take any sequence of correlated equilibria of this sequence of game. Call mu n the distribution of flow that it induces. All right? Mu tilde n, that's a correlated equilibrium, which means that that's a distribution of our action profile. There is a mapping, x of A. This mapping maps action profile into action flows. So if you have a distribution of our action profiles, there is a push-forward measure mu n on the set of flows. All right? So this set of flows mu n is a distribution of our flows, and the result is that any accumulation point of this sequence is a correlated equilibrium in our sense. All right? And we are we are in compact set, so we know that there are accumulation points to those sequences. So can I do that?
No, wait.
Okay, yes. Okay, so here's the proof. Let's write the incentive inequality of the correlated equilibrium. So this means that take any player I, take any two pair of actions. My expected cost when I am told to choose action E is less or equal to my expected cost when I am told E, but I choose B instead. Okay? So what's different from the correlated wardrop equilibrium is that my weight is not zero. So this is what's going to happen. This is my expected cost on the event when I am being told to choose E, and this is the cost that I'm going to get. Now, suppose that I deviate to B instead. I need to add this term because I'm going to add a weight Wi on action B and subtract it from E, right? Okay, so this is the correlated equilibrium inequality. Multiply this inequality by Wi, sum this over I, and you get this inequality here. Now, so here is the inequality that we get. And now, if you look at, for instance, the left-hand side, you calculate this expectation, and you take the expectation of the conditional expectation given the flow x. So this is what you get given the flow x. And here you see that you have the probability here that the flow is x. And here, what do you have here? You have the total mass of players who choose action E. That's exactly XE. So you have the expectation of this term XE CE of X. And now this is where mu n intervenes. And when n goes to infinity, you converge to this term. Okay, so already on the left-hand side of this inequality, I have the left-hand side of the correlated wardrop equilibrium inequality. The same goes for the right-hand side, except that there is an error term. Okay, so I'm going to so I have the cost of action B, but I have this weight here. What I would like to have would be the cost of action B, but then I have this error term here. So this first part converges. So the only point is to say that the error term goes to 0, and that's basically by uniform convergence. Because in this you have CB of x plus Wi minus CB of x, and when Wi goes to 0, uniform convergence here says that this goes, the error term goes to 0. All right? Yes. Okay. All right. So now, so what's the where are we? What I've shown you, what did I show you so far? Definition of correlated equilibrium, an example where a correlated equilibrium improves, right? And the fact that this notion of correlated equilibrium is justified by the limit of finite games. All right? So now I'm going to study a class of games to give some more properties on class of games, and basically I will go towards somewhat what you can see as a negative result, is that I'm going to say under some condition correlation does not improve upon Nash. And that is going to be like this. So I'm going to say that we have a potential game if the vector of cost function CA of x is the gradient vector of a function capital phi, which we call the potential function. Okay? This notion of potential games, again, is used a lot in all the theories of learning. And again, I can refer to the book by Sandholm, where all these definitions are made really clear. Okay. Any congestion game, network routing game is a potential. Here is the potential function. This is the sum of the anti-derivatives of the cost function like this. Yes, in a typical congestion game or routing game, cost functions are increasing. So you see in this expression, and again, this is the case of a congestion routing game where the cost function are functions of one variable, just what is the number of cars on a specific edge, okay? So in particular, it is typical to assume that these functions are increasing. The more people on the road, the longer it takes to drive. And then this means that the potential is a convex function, okay? So I'm going to give a result in a moment when the potential is a convex function. And of course, what is the case where the potential is a convex function is when the derivatives are all increasing. But of course, this is a little bit more general than that. It is easy to see, and I will give you an example with the alpha roll bar, that any game with two actions always has a potential. Okay. So, sorry, I'm going to have this again. If there is a potential, if we have a potential game with a convex potential, then the set of correlated equilibria is a convex hull of all the Wardrop equilibria. Namely, that you cannot improve if you want to minimize the total cost or to minimize another functional on that. You cannot improve upon, or if you minimize any linear functional on this set, you cannot improve upon minimizing of a Wardrop equilibria. Yeah. This was a little bit, we found this a little bit surprising. The other result in this direction is a paper in the International Journal of Game Theory by Neyman in 1997, where you have finite set of players. You have every player has a convex set of strategies, and there is a potential in the n-player game, and he proves the same where the set of correlated equilibria is a convex hull of the set of Nash equilibria. We have been puzzled and we have been thinking a lot about the similarities between these two results. There is some similarity, but some differences. We can describe them. I'm not sure we understand them fully, but we can describe them. So I'm not going to go into that detail, but in fact, here, in our case, this is even equal to the set of coarse correlated equilibria. Okay, I'm not going, if you don't know what that is, forget about it, but for those who know learning and no regret matching, this has to do with coarse correlated equilibria. In Neyman, that's not true. The set of coarse correlated equilibria could be larger. Here it cannot. Okay, so how much time now? Just to see if it's worth it to show you the proof. 15 minutes, so maybe I don't show you the proof. It's a nice proof, and I'm happy to share the slides if you want to have it and to read it. This uses the variational inequality for characterizing Wardrop equilibria, and the fact that the costs are the gradient of the potential function, and then when you write the convex inequality, where a convex function is always above the tangent, then you can see the difference in the potential with the expected cost, and so it's a natural proof. Anyway, let me skip that and show you a little bit of the rest. Okay, so this gives a corollary, which is that suppose that we have such a game of convex potential. In particular, if you have a congestion game, network routing game with increasing cost, which is a particular case, then if you take the n-player game, all the flows of correlated equilibria are going all to converge to wardrop equilibria. That was not known before. There is a recent paper by Scarsini, Cominetti, and others who showed that all the Nash equilibria, all the distribution induced by Nash equilibria of the n-player game converge to the wardrop equilibria. But here we get more. We get that all the correlated equilibria converge to the wardrop equilibria. For fixed n, even in a congestion game, there might be a huge difference between what a Nash and a correlated equilibrium does. So in a paper by 3 co-authors, Ashlagi and 2 other co-authors, which I forgot, they give example of a congestion game with finitely many players where the correlated equilibrium is so much better. What's the idea? Imagine that you have 2 roads, one which is super slow but super wide, so you're sure never to have any jam on it, but it takes a lot of time. And one which is super fast, but it's extremely narrow, in the sense that only one car can go. So what does that mean? A Nash equilibrium is going to be extremely bad here, because everyone is going to compete for being the only one on the road. So in a mixed equilibrium with positive probability, there will be 2 people on the road. And then whenever there are 2 people, this fast road is going to becomes extremely bad. Okay? So correlation avoids that. The mediator would decide randomly who has the chance to be alone on the fast road, right? But without correlation, with mixed equilibrium, there are going to be several people on the same road, and it's going to be very bad. But this example works only for finitely many players, for a fixed number of players. If for the same continuous cost function, you increase the number of players, but you keep the same continuous function, then our results show that this does not survive when you get send n to infinity.
This means only extreme points of somehow make sense. Because here, convex potential, since it's the convex envelope, let's say, of the equilibria, that you go only to extreme points.
If you're minimizing some functional, and then you would go to the extreme point. That's what you mean?
Yeah. You don't go to the convex combination between two wardrop equilibria. This is what you mean here. Correlated equilibria in the finite game. Yes.
So
that you don't go to the convex combination, so strict convex combination between wardrop equilibria.
I see what you're saying. I don't know. When you have a game with a convex potential, the set of wardrop equilibria is a convex set.
Yeah,
it is a set of minimizer of the potential. This is a convex set.
But I think the set of wardrop equilibria also will be convex.
Yes, that's what I'm saying. That's what I'm saying.
So in your results before, when you said delta of WE, in fact it's WE.
No, because it does not live in the same space. WE is a set of flows, right? The set of correlated equilibria is a set of distribution of the flows. It's not exactly in the same space. So the expectation, yes, you have a set of wardrop equilibria, you have a distribution over this convex set, so the expectation is yet another wardrop equilibrium. Okay? So morally, you're right. morally you're right. That's the same. But they are not in the same space. In many applications where you have strictly increasing cost, the wardrop equilibrium is unique and it does not matter. Okay, so what happens in the game of El Farol? Because in this game, I have shown you by example that correlated equilibrium does better. It is a potential game. Any game with two actions is a potential game, so it must be that the potential is not convex. And indeed, it's not convex. It looks like this. Okay. It's interesting to see the shape of the potential and to see where the one-drop equilibria are. Again, if you go to the book of Sandholm, you would see that the one-drop equilibria, they are the Kuhn-Tucker point of the potential function. So here you have the two interior extrema, and you have the local minimum here. Okay. So that's only part of our work. I wanted to mostly talk about that. But then we can extend to incomplete information like this. So take the same, except now that there is an unknown parameter theta, which is distributed according to some commonly known probability distribution P. And cost function, they depend on theta as well. So now we extend the definition. We call that base correlated wardrop equilibrium. Mu now is a mapping from theta to distribution over flows. So what's the idea? This represents a mediator or a recommender, a recommendation system that observes theta, observes the state of the world, and conditional on the state, issues recommendation. Otherwise, apart from that, the inequality, the incentive compatibility inequality is exactly the same. That's the expectation of what you're going to get as a cost when you're being recommended A, and that's when you play B when you're recommended A. So if you write that in terms of expectation, that does not change anything. The difference is that now the distribution of our flows is conditioned on the state theta. For simplicity. For simplicity. I think that's not the easiest part. That's not the easiest part to relax. It would be easier to relax the finite actions. I don't know if I can, but I think that relaxing finite states is much more difficult. In particular, in terms of, again, what are the information structures? How to describe the information structures? But I don't know. We didn't try.
For actions, you have for every A, B some inequality.
Yeah, you would have to need to replace that by some every measurable functions from A to A or something like that. Yeah, that would be technical as well. I agree. Okay, so we can extend, and I'm not going to show you the proof because it's the same. We can extend the convergence result. So this concept, this is the limit of all base correlated equilibrium distribution of the n-player game. What's a base correlated equilibrium distribution? That is the Nash equilibrium distribution of some n-player game for some information structure. So take the n-player game with incomplete information. Take any possible information structure that you can think of in the n-player game where everything is finite. Here you can list all the possible information structure. Look at all the distribution that you can generate by all Nash equilibria of all this, and this is a set that has been called in the literature base correlated equilibria. And now if you look at all those guys, and you let n go to infinity and the weights go to 0, then this inequality up here converges to the incentive inequality that I wrote before. So, but that's the same proof. Technically, that doesn't change much. Okay. So now, I mean, in terms of application, that's really the model that we had in mind to begin with, right? With my co-author, we say, let's try to understand the case of complete information, because if we don't have a good idea what to do with complete information, how are we going to know to treat incomplete information? So that's why there is this first part, we first work on complete information. But that was the motivation to begin with. And now think of, again, delivering information to drivers. There are two types of information system that people have thought of in the literature. One is public information, like you tell everyone the same thing about driving condition, so everyone has the same belief. That's one. Or you give them independent signals. You draw IID signals and you give independent signals to different people, right? But what's IID when you have a continuum set of players? Mathematically, I don't know. Don't ask me. I'm sure there are people who know a lot more on probability than I do, and they would know how to define that, but let's say that I don't. Intuitively, we can say that continuum of player, there would be a fixed proportion of people who receive signal 1, signal 2, and so on, like some exact law of large numbers. So we call that a simple equilibrium, but that's the idea of IID, namely that given theta, the mediator chooses one deterministic flow profile. So it recommends a deterministic number of players, xa of theta, to go A, and deterministic number of players to go B, and so on and so forth. And so in the burgeoning literature on this topic that we have read basically in the COVID period, there was a lot of examples that were hanging around. And there was a sort of debate whether it would be best to have public information, to have IID information, and whether in these games which are so symmetric, whether one or the other would be optimal and you don't need to look for more. Bottom line, and if I don't have time to go through the end, bottom line, public is not enough, IID is not enough, and you need to go for more general in some cases. So here is the example. This is a conference paper of 2017. So this is this example. It's a congestion game. Everyone goes from origin to destination. A is the up route, B is the down route. What's the cost of taking route downwards? The route B, that's 1/3 plus 2 times the number of people who go B. Okay? So the congestion time, the travel time on this is I find increasing function of xb. Up there, it's constant. It's constant, but it's either 0, like it's super fast, or 1, like it's super slow. But it does not depend on, right? Okay. The idea of Wardrop is that in equilibrium, all routes are equally congested, okay? So if you think that the probability of theta equal 1 is 1/2, the expected cost over theta is 1/2. So this is the cost in equilibrium. And now it is easy to check that whatever public information system you use, the expected cost is always 1/2, always. But an IID flow would be better, Namely, when the state is 0, you send everyone up there. When the state is 1, you send 1/6 of the population down there. Of course, it has to be somehow random, right? It must not be that one player knows whether it will be always recommended to go up and to go down. So in this 5/6, 1/6, you need to draw at random which subset of size 1/6 is going to be sent down and be sent up. Okay? And it can be shown that in this example, that's the best that you can do. And this is implemented by IID signals. Okay, maybe, yeah, I need to stop soon, right? Yeah. Okay, so I'm going to skip that, all this, and I'm just going to show you an example, and I'm not going to give you the detail of the example, but basically, we have been thinking about that, and we came up with this example, and there are others. Since then, we found others, and other researchers found others, where public information is not optimal, IID information is not optimal, and you need to have some randomization between the two. And so here, yeah, that would be a slightly more complicated network. So basically, you look at this. So it's very cheap to take this B arc. It's very cheap to take the C arc unless the number of people is too high. Okay, so basically, optimally, you would want to send a lot of people, 1 minus epsilon people, proportion of people on the C arc. Okay, but then if you look at this arc BC, then it's okay, it's a medium value, but then it becomes strictly concave. So you look at the function on the blue arc, is going to be some value, and then it becomes strictly concave. And this is the strict concavity of this function that is going to say we need to randomize. So basically, when you have this strict concavity of the cost function, when you take the convex combination on the strictly concave part, you get on average something which is less. So that's why you want to randomize, the mediator would want to randomize between sending 1 minus epsilon people there or 1 there. And that depends on of course, on what happens on root A. So I'm not going to give more details on this example. And again, there are examples which are either simpler in terms of network, but more complex in terms of cost function. So if you take very simple networks with very simple cost functions like affine, basically you're not going to find the counterexample. So the counterexample we found always takes some complexity to reach, but okay. Yeah, I think it's better to stop here. Thank you very much.
Any question from people connected? If there is anyone connected who wants to ask a question, don't hesitate. Switch just on your microphone. Or someone in the audience. Nobody wants to ask a question? I will ask. So can you give us a little summary of what you do in implementation? Because I'm curious.
We use some work that has been done in this paper, in which an operations research paper of 2020, where, like I said before, it's difficult to exhaust all the information structures. So let's consider just simple information structure. So what would be a simple information structure? You take the population of size 1, you cut it in subpopulations of finite size, lambda I, finitely many population, And then you treat those populations as a single player, in the sense that conditional on the states, you draw a signal correlatively for every population, and you distribute that signal to this population. So it's semi-public. It's like the signal is different across the subpopulation, but it's public within the same population. Okay? And now, what they do in this paper is that they let the players arrange themselves. Like, they have now this information Ti, population I, and now they spread out on the rows whenever they want, and you write some wardrop equilibrium condition. So what we show is that whenever we have such a solution, from our concept, first we start with some approximation. We approximated this distribution of flows, we approximated by something with finite support. We know that the distribution with finite support on the set of probability distribution over a compact, this is dense. So first you can approximate with finite support. Then in the support, you approximate all the flow with rational numbers. You need rational numbers there. Mm-hmm. And when you have rational numbers, then you can construct the information structure and the equilibrium like they did to implement what we want. And what's interesting is that we recover some form of revelation principle, in the sense that we can have the signals, they are just action recommendation, and in equilibrium, people would obey the recommendation. So that's the first weak implementation result. And if on top of that, you have a strictly convex potential, which happens when you have strictly increasing cost function, then you have basically a sort of strong implementation result, because you have a uniqueness of the equilibrium flow. Mm-hmm. So, yeah, it's not. I mean, it's a little bit specific type of form of implementation, but at least what we like about it is that in those cases where you have strictly convex or strictly increasing cost function, at least you can have a sort of strong implementation result, like you make this recommendation, and it would be the unique in the unique equilibrium outcome, they would obey the recommendation. So that's what we know.
Thank you. Thank you. So let me stop here and thank the audience and thank the team that recorded this meeting. Thank you, and thanks to everybody.
Thank you. Thank you.
Tristan.